when we're doing a bridge like the bridge we're building now, Randselva Bridge, I guess 90-something% of the bridge, that's things that we produce ourselves, concrete and reinforcement, and to a certain degree tendons. But then we have things like we show in green here. We have a joint, and a joint it's very important that it's fitted correctly. And normally you'd only have 2D drawings to do this. And in a complex structure where you have a lot of reinforcement as well, it's quite hard to foresee everything that might clash. So getting a good 3D model from the deliverer is very important. In this case, it's Maurer, and they've provided us with the IFC file. That's been very, very useful. So having a look at the same joint just in different ways of displaying it, we can now very clearly see what we need to adjust to make this fit the structure. The good thing here is that, or rather the difficult thing here is that when we start the project, we have no idea who the deliverer is. So we need to reserve some space, but we do not want to reserve too much space, because then we cannot finish any of the pouring stages next to the joint. Another example is the free cantilever parts. So this is the bridge. The joints we had a look at, they're located at the ends of the bridge. So here in axis 1 and in axis 8. And for example, when they start building this part, then they do the hammerhead first, and then they build the first segments on either side. And to build these segments, they need
formwork.
Yeah,
formwork.
Correct. So you'll have one of these on either side of the structure. And the forces and the weight of this is quite large. So we need to hold them in place, and we do that by making holes in the concrete. And those holes have been, from our side, they're symbolized by these marks. And here we then get a very detailed 3D model of the deliverer of the scaffolding, the product, that we can then, for casting of the second segment, then I can very easily and visually check whether the holes fit the holes that I've made in my structure. Because it would be quite devastating if we had to start drilling new holes here. And here we see they fit perfectly at all the stages where I need them to fit. And if we go down here on the lower end, we also see that we hit the holes that we anticipate. So this is a beauty of the BIM design and 3D design. We feel we have very good control over things that would be very hard to do in 2D. And then if we have a look at again, here's the joint that we had a look at.
What is the joint made of?
Steel and rubber, because this the thing is the abutment that's built into the into soil, so that doesn't move at all. But the bridge itself expands with heat. So
and contracts.
Yeah.
It's a fugue, right? What is the word in English?
Joint in English, fugue in Norwegian. Yeah.
Okay.
And we can then have a look at, for example, reinforcement. We can then see quite easily what needs to be done. Does it clash with anything we've made so far, and what needs to be adjusted for this to fit, and what bars need to be added so that the joint is properly connected. So having when you write these contracts on third-party products, we see an importance for the people manufacturing and building to have good contracts where it states that the third-party deliverer needs to deliver their product in 3D BIM models. That's getting more and more important, because if you only had these 2D drawings like these ones, you would very easily get a surprise at site. Of course, it's been done for hundreds of years, and they've managed, but the quality control that you're able to do now is unprecedented.
Yeah, that's not an argument. Like that would be a reason not to improve at all. So if we have a better solution, like we definitely must employ it. Like it will lead to more security for people who are working. Not forget about this, the very important aspect: saving money, and building it quicker, maybe, right?
Yeah.
So yeah.
No, I agree. And then we'll have a look at smaller projects. This is a small. Well, it's relatively small. It's about 4 or 5 meters high. It's corner foundation, 1 of 4 in a structure in a building, and it's concrete, and there's some quite enormous forces going into this structure, but it's relatively small in width, and from a 2D drawing, we see that there's enormous amount of reinforcement needed in here. And when you're doing the design for the reinforcement, it's very, very hard to see in 2D drawings if this is going to fit or not. So if we were then asked if we could do a 3D model of the reinforcement, and we'll have a look at the model here now. Let's see. If we see here now, it's packed with reinforcement. It's really, really hard to make it all fit. It's we worked a number of hours to make this fit, and of course we see some small clashes, but we knew that we're going to be able to do that.
It's going to be very difficult to pour the concrete here.
Yeah, but I'll show you pictures because it's already been casted.
Yeah, okay.
So let's see. This is how difficult it is to fit.
Oh, Jesus Christ.
But
like you need to use a syringe to try to.
Yeah, but without the 3D modeling, it would be a lot harder, because here you have in some of the sections you have 5 layers that want to compete for the same space.
Yeah. Well, if you don't have, like how I think here, like if you don't have the 3D model, there might be a possibility that you cannot build it, because you did here when you did it in 3D, you see that you have place. If you encounter a challenge, you try to fix it before you did that, right? Imagine being there, being forced to fit all this, and you cannot do it. Just stop the entire crew working and try to find a solution, right? How much expensive is that to do?
Definitely. And as you see, this is a test casting, but it looks beautiful. And again, if we see some of the layers here, for example, this one, how we have to how we skew them to make it all fit.
But regarding the one clashing, like what is the thing with them?
The ones that we saw clashing down here?
Yeah.
Well, these ones, when you model them, you can start bending them separately, but as often as possible, you want a rebar to be part of a group.
Mm-hmm.
You don't want to explode it, so every rebar is unique. So if you can see from your design that clashes are solvable, then allowing small clashes like this, it's okay, because you can see that if I tilt this a little bit, we will have space.
So what is the measure? What do you do then to be sure that it won't be a clash on the site? How do you fix this?
Well, on this side, I can show you quickly. Let's see.
But before, in the first place, if you would not have a 3D model, you would not have seen this.
Definitely not. And I'm sure they eventually would fit it all, but it would take a lot of manual labor, because what we're able to do now is we can do automatic rebar takeoff with bar bending schedules, so that a machine can bend all these rebars automatically. And then we do sequence like this, so that people at site know which ones, which of the bars goes first.
Yeah. Oh, okay. So you from up down, you just have it in the order how they should place them.
Yeah, at least our suggestion on how they should place them.
Yeah, sure, I understand. But nice, very nice.
Yeah.
Well done.
Thanks. And then on an information takeoff, we can automatically take out bar bending schedules, and say if I only wanted to take out rebars for the lower part, then I'd just mark these ones, and then do a bar bending schedule for those. And then maybe tomorrow I could do another one of the top one. So it gives you quite a lot of flexibility on large projects, especially when you want to order things.
And do you make any notes in the bar bending schedule for the series of bars that you could not fit in the 3D model, or how do you exactly you handle this?
We could do that, yeah. So if we have a look at this one, when we have a number of attributes that we've attached to every object, and here we have a number of open comment fields that we could add attributes or information if needed. In this case, we've only had we haven't added much information, because there was no need to. But on the Ranselva project, we have a lot of information there. Yeah. So so the casting was I was very impressed by the shape of these. So
yeah, it looks like art.
Yeah, it does, doesn't it?
Yeah.
An interesting comparison between the this is the hammerhead of Ranselva at Axis 2.
Yeah.
And then we see what it looks like at site. So it's fun when things matches, and we clearly see here how they've used the information at site to build exactly what we plan. And it's been mentioned before, but we are of course very proud of that we won the Trimble Global BIM Awards for Best Project in the World 2020. And the last time someone won, it was this project. It was the Museum of the Future in Dubai. So that says something
really
about
nice company. A really nice company to be a part of.
Yeah, it was